by much if it's a continuous and differentiable function. So that the integral over the red curve going this way and the integral over the blue curve going this way are very nearly equal and opposite. Now I'm talking about the integrals over these two little bridging points that bridge from the curve C to the curve C1. So I can claim that in the limit, the integral in this direction and the integral in this direction are equal and opposite. That is, as the separation approaches 0, the integrals along these segments approach equal and opposite, so they make no net contribution to the overall integral. And the missing part of C1, because we got a little segment of C1 that's missing here, and a little segment of, little segment of C that's missing here, little segment of C1 that's missing here. The missing segments approach 0 length and become negligible. So that the integral around our entire path, the the integral over the closed path that originates here and terminates here, the path that goes around here, cuts over, goes backwards around C1, comes back, and continues going in the positive direction around C. Will be just the integral around C minus the integral around C1. So we have a closed path which starts and ends here. The integral over the closed path of f dot, I almost wrote delta, matter of fact I started to write delta, f dot ds equals 0, but that integral also equals the integral of f dot ds over C, the curve surrounding the region R, minus the integral of f dot ds around the curve C1. Well, this integral is around a circle about the origin, so we know that this is 2 pi. These two give us 0, which means that this integral has to be 2 pi. So that we have 2 pi minus 2 pi, which gives us 0. So that writing it a little bigger here, the integral over our entire closed path of f dot ds is 0. So the integral of f dot ds over c minus the integral of f dot ds over c1 equals 0, so that the integral over c of f dot ds has to equal the integral over c1 of f dot ds, which has to equal, as we've again proven previously, has to equal 2 pi. And this proves the result that we set out to prove, that if C is any decently behaved curve. Now, we haven't really talked much about what decently behaved means, but C is any decently behaved curve containing region R, bounding region R, then the integral of this function over that curve has to equal 2 pi. So that we've generalized the idea that the integral around a circle has to be, a circle centered to the origin for this function has to be 2 pi, to the idea that if we deform this region in some way to obtain any curve, any decent curve about the origin, that this integral still has to be 2 pi. This becomes a really big idea. It's Cauchy integral formula, essentially, in functions of a complex variable. Something you're not likely to be aware of right now, but something that really is a big deal and a very, very powerful set of tools.